Hey everyone, and welcome to this explainer. Have you ever looked at a simple cardboard box or maybe a metal tray and wondered, are we actually getting the absolute most volume out of the least amount of material here? It sounds like a simple question, right? But in the real world of manufacturing, answering that question correctly can save companies millions of dollars. It's a quest for perfect efficiency, and it's heavily tested in your coursework. Today, we're going to transform a few seemingly simple geometric puzzles into a fascinating journey of mathematical optimization. We'll start with manual calculations to understand the core concepts, and then we'll see how injecting a little information and communication technology, or ICT, can completely supercharge our math. Before we continue, I want to quickly remind you to subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now so you don't miss out on these essential strategies.
Okay, so let's dive into our game plan for today. We have 4 distinct optimization challenges to conquer. First, we'll look at maximizing tray volume. Second, we're going to flip the script and look at minimizing packaging. Third, we'll tackle what I like to call the paper cone puzzle, which brings in some really cool 3D geometry. And finally, we'll wrap up with the power of spreadsheets, where we let technology do the heavy lifting for us.
All right, let's jump straight into Section 1, Maximizing Tray Volume. Our objective here is finding the absolute perfect cut for a 30 by 40 centimeter sheet.
To really grasp this, I want you to ground this abstract math in a physical reality. Imagine you are standing in a workshop, holding a completely flat rectangular piece of sheet metal. It's exactly 30 centimeters wide and 40 centimeters long. Now, to make a functional tray out of this flat sheet, you obviously need walls to keep things from sliding off. So you grab a pair of heavy-duty metal snips. Your task is to cut 4 identical, equal-sized squares out of each of the 4 corners of that rectangle. Once those 4 corners are completely removed, you fold up the remaining rectangular flaps along the sides, and voila, you have just built an open-topped metal tray. But here is the massive mathematical catch. The precise size of that little square you just cut out entirely dictates the final dimensions and, most importantly, the total volume of your finished tray.
Let's actually run the numbers and look at the math if we were to do this manually. What exactly happens if we cut out a tiny 1 centimeter square from each corner versus a slightly larger 2 centimeter square? If you cut a 1 centimeter square, you have to remember that you're taking 1 centimeter off both ends of the length and both ends of the width. So your original 40 centimeter length loses 2 centimeters total, becoming 38 centimeters. Your 30 centimeter width also loses 2, becoming 28 centimeters. And the height? Well, the height is just the 1 centimeter flap you folded up. Multiply 38 by 28 by 1, and you get a volume of 1,064 cubic centimeters. Now, what if we get bolder and cut a 2 centimeter square? You lose 4 centimeters total on each side, so your base shrinks down to 36 by 26 centimeters. But look at the height, it doubles to 2 centimeters. Multiply 36 by 26 by 2, and suddenly your volume shoots up to 1,872 cubic centimeters. So the really crucial takeaway here is that even though the physical base of the tray got smaller, the increased height more than made up for it, giving us a drastically larger volume.
But here is exactly where we hit a mathematical wall. We clearly saw the volume go up when we moved from a 1 centimeter cut to a 2 centimeter cut. So will it keep going up at 3 centimeters? What about 4 or 4.5? Logically, at some point, the base is going to get so tiny that the volume has to start shrinking again, eventually hitting 0. Manual trial and error only gets us so far before it becomes incredibly tedious. The manufacturer's ultimate million-dollar question is, what is the exact side length, down to 1 decimal place, that produces the absolute greatest volume? To answer that, we need a systematic way to find that peak. Keep that thought in the back of your mind because we are going to solve that exact type of problem using technology a bit later. Stop scrolling for just a second. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve their understanding of these exact concepts. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Moving right along to Section 2, Minimizing Packaging Material. I call this one the tennis ball dilemma.
For this challenge, we are completely shifting gears. Instead of trying to maximize the empty space inside a tray, our goal flips to minimizing the physical material on the outside of a package. Here is the scenario, derived straight from our core source material. A sports manufacturer is packing tennis balls. These spherical balls have a precise radius of 3.3 centimeters. That means each ball has a total diameter of 6.6 centimeters. The manufacturer needs to create a cuboidal container, which is basically just a standard rectangular cardboard box with a lid that is designed to hold exactly 12 of these tennis balls. But here is the catch, and it's a big one in business. Cardboard costs money. The manufacturer wishes to pack these 12 balls using the absolute minimum amount of cardboard possible.
So you really have to think, how do you arrange exactly 12 tennis balls? You actually have several different mathematical options. You could line them all up end-to-end in a single super long tube, a 1x12 arrangement. Or you could pack them in 2 rows of 6. Or you could make it even more compact and do 3 rows of 4. And this brilliantly illustrates how different mathematical layouts drastically alter the total surface area you need to construct the box. A long 1x12 tube requires a wildly different amount of cardboard compared to a compact 3x4 box. And the crazy thing is, both boxes hold the exact same internal volume. They both hold exactly 12 tennis balls. But the geometry of the arrangement completely dictates the surface area. Generally speaking, the closer a cuboid gets to being a perfect cube, the less surface area it requires to enclose the same volume.
To truly solve this in an investigation setting, you can't just take a wild guess. You have to be incredibly systematic. First, you need to sketch out these different cuboidal containers. Then, using that 6.6 centimeter diameter of the balls, you have to calculate the exact length, width, and height of the box. Next, you compute the total surface area of all 6 cardboard faces combined. But the quest for optimization actually doesn't stop there. The source material notes that a truly innovative manufacturer might even consider other flat-face containers. What if the box isn't a rectangle at all? What if they use a hexagonal prism, kind of like a honeycomb structure? By mathematically investigating all these different surface areas, you can scientifically recommend the single most economical, money-saving design.
Let's move on to Section 3, the paper cone puzzle. This is where we start connecting 2D sectors directly to 3D dimensions. We've looked at folding rectangles, and we've looked at packing cubes. Now, let's step up the mathematical complexity and dive into curves and 3-dimensional geometry. I want you to imagine you have a perfectly flat paper circle with a radius of exactly 10 centimeters. Now, you take a pair of scissors and cut a wedge or a slice out of it, exactly like taking a slice out of a pizza. That slice you remove is mathematically defined by its sector angle, which we refer to as theta. When you pull the remaining edges of that cut paper circle together so they touch, it pops up into a 3D cone. Here is the truly mind-bending part of this investigation. The size of that slice you remove, meaning the exact angle of theta, completely, 100% dictates every single dimension of your newly constructed cone. By changing that one angle, you change the cone's base circumference, its base radius, its vertical height, and ultimately, its total internal volume. It is a brilliant example of mathematical variables interacting in real time.
Which brings us to our final core topic, Section 4, the power of spreadsheets, automating math with ICT.
Now think about the cone we just talked about. Calculating the radius, using Pythagoras for the vertical height, and then calculating the volume manually for every single possible sector angle is absolutely exhausting. It would take days. When manual math hits a wall like this, information and communication technology instantly steps in to solve our heavy lifting. Instead of calculating one single angle at a time, we've set up columns in a spreadsheet. As you can see, column A is the angle of the sector, theta, starting small at just 5 degrees. The spreadsheet then uses formulas to automatically calculate the sector arc length, which magically becomes the base circumference of the cone in column C. From there, it finds the new base radius, calculates the vertical height, and finally spits out the exact volume in column F. Just look at how the numbers behave. At a tiny 5-degree angle, the volume is a minuscule 0.202 cubic centimeters. By the time we increase the angle to 15 degrees, the volume has already jumped to 1.816. The spreadsheet is doing all of the complex trigonometry and spatial geometry absolutely instantly. By carefully entering the right mathematical formula just one time, we can scale this entire investigation effortlessly. We simply click and drag the formula down the spreadsheet rows to calculate the dimensions for angles all the way from 5 degrees up to 355 degrees. Think about that. We generate hundreds of complex data points in a fraction of a second. But let's be honest, just staring at a giant wall of numbers isn't the best way for the human brain to understand optimization. The next logical step in our ICT activity is to use the software to plot a scatter or line graph. This allows us to actually visualize how the volume changes over time, allowing us to pinpoint the exact peak where the maximum possible volume is achieved.
So I want you to imagine that graph forming in your mind's eye right now. How exactly does the volume change as that angle theta increases? It doesn't just go up in a straight line forever. It creates a fascinating sweeping curve. Think about the physical paper. As you cut a larger and larger slice out of the circle, the resulting cone gets taller and pointier, which naturally increases its volume. But simultaneously, because you are removing paper, the circular base is getting narrower and narrower, which decreases the volume. It's a mathematical tug-of-war. The graph will steadily rise as the height advantage wins, hit a beautiful, mathematically perfect peak, and then it will steeply fall off as the shrinking base takes over. That exact peak on the graph, that is our optimized answer.
And that really brings everything full circle for this topic. Whether you are a factory manager folding metal trays to hold the most liquid, a sports company trying to save money on cardboard for tennis ball packaging, or a student cutting paper cones to find the peak capacity, the underlying principle remains exactly the same. Manual trial and error is a fantastic starting point to understand the physical reality of the shapes, but combining highly structured mathematical formulas with the sheer computing power of spreadsheets is the ultimate key to real-world optimization. It takes all the guesswork out of efficiency. Students who implement these mathematical strategies effectively see massive improvements in their logical problem-solving skills, but only if they practice consistently. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by without having these strategies locked down.
We've seen firsthand how a tiny millimeter change in a corner cut or just a few degrees difference in an angle can completely transform the efficiency of an object. So I'm going to leave you with a challenge to test your new perspective. Take a look around your room right now. What everyday object, shipping package, or plastic container are you looking at that might be wasting material? What could be mathematically optimized right this second using the very principles we just covered? Drop a comment below with your target grade for mathematics and the biggest challenge you're facing with topics like mensuration and optimization. Our team responds to every single comment. Like and share this explainer with a study partner who needs it. Ace the Exams. Your Cambridge success starts here. Keep asking great questions and keep optimizing your world. I'll see you in the next one.